Can you see my screen?
Yes, sir, it's visible.
So fluid mechanics lecture 4, right? So today's topic of discussion is pressure and its measurement. So shall we start? Tell me, shall I start or should I wait? Hello.
So students are still joining in, so
Okay. So maybe for next 1 or 2 minutes we'll wait and then we'll start. So just revise what we did in last lecture. I hope you must have solved the numericals which I asked you to solve. That capillary rise in case of gap between two concentric tubes, and also the numerical on the blade, one side, one edged blade and the two edged blade. I hope you must have solved those numericals. Right now 32 students are there. I think we should start. Okay, fine. So moving further, today we'll talk about the pressure and how to measure the pressure, or what are the instruments used to measure the pressure, right? So before we proceed further, let us talk about few concepts like what is hydrostatic condition. Now I'm going to talk about hydrostatic condition. Now look at the diagram, pay attention. Just waiting. Oh. So see, what we are going to do is we will define what is hydrostatic condition now. Hydrostatic condition. Now for that, what I have done is I am going to take a small fluid element like this, fluid element in a static mass of fluid. Now this is the free surface of the fluid, this one, free surface, and I am taking one the fluid molecule from this mass, and what is done is the pressure distribution at the top edge of the element and the bottom edge of the element is shown, right? So this basically denotes the magnitude of the pressure, you can say, acting at the top face, and same way at the bottom face. Now if you look at the diagram carefully, this length is bigger compared to this. Now why it is like this? It is drawn intentionally because we don't know whether the pressure at this point or this level will be more or not. So time being, we just remember this length is more than this, right? So I am considering a small fluid element like this, and then I have shown the free body diagram for that element, and what are the forces acting on this element are shown in the free body diagram. So same fluid element or the fluid particle, and then there are basically two types of forces acting in this situation. One is the self weight of the fluid particle, which will act in vertically downward direction through the this CG of this molecule or a particle, and as there are two pressures acting, one at the top and at the bottom, so the net effect will be the net outward pressure or the net force because of pressure, which will be acting in vertical direction, right? So two types of forces are acting on this element. Now under equilibrium condition, this fluid element or fluid particle will remain at the position where it is right now uh, when these two forces balance each other. When the weight of the fluid element or fluid particle is balanced by the net force, pressure force acting in vertically upward direction, when these two forces are balanced, the fluid particle is in the position where it is right now. Is that clear? So what we mean by hydrostatic condition then? The hydrostatic condition means that each fluid particle is in equilibrium with the net force due to pressure balancing the weight of the fluid particle. As simple as. I repeat, the hydrostatic condition is, or hydrostatic condition means that each fluid particle is in force equilibrium with the net force due to pressure balancing the weight of the fluid element. Right. So now it is time to talk about the term pressure. What is pressure? What is pressure? You must be knowing what is pressure
Force
or
per
not.
unit area.
Huh? Force.
Force per unit area.
Force per unit area. So is stress, no? Stress is also force per unit area, right? Or not? Stress is also force per unit area. Pressure is also force per unit area. So is it that the pressure and stress both are same, one and the same? So let us find out. Now, so we will define the pressure. Now, before you look at this definition, wait for some time. So consider, let us say, I am considering a soccer ball like this. Consider this as a soccer ball, and there will be air inside this ball, and because of the air distribution inside this ball, see, this air will be applying some sort of force on the wall of this ball, right? Everywhere like this. So this is the, what you can say, the pressure distribution created because of the air inside this ball, right? So what I'll do is I will take an element, small element here, small element having the area delta A, right? And the force which is acting normal to this delta A, so this force is nothing but, I will call it as a delta F normal, right? So if I use this elemental approach and if I define the pressure, so it will look like this. So the definition of pressure is magnitude of normal force per unit area. Magnitude of normal force, remember this. This is not simply the force per unit area. Intentionally it is written magnitude of normal force per unit area at a point due to fluid. So this is happening because of the air distribution or the pressure distribution created by the air inside the ball, right? So the pressure is defined as the magnitude of the normal force per unit area, and using the limits I can define it like limit delta A tends to 0. So this area which I have selected, I can select a very small area like this, and if that is the case, then this delta A is tending to 0, so that we know. So under this limiting condition, the pressure can be defined like this: delta F normal, limit delta A tends to 0, delta F normal divided by delta A. Or in differential form, if I write it, it can be written like dF normal divided by dA. So I can write it like this also. So hereafter, remember the definition of pressure. It is not just the force per unit area, rather you should say as the magnitude of the normal force per unit area. Now why we are saying magnitude of normal force? Magnitude of normal force. So for that you have to answer the question whether pressure is a scalar or a vector. Pressure is a scalar or vector. What do you think? Whether the pressure is scalar or a vector? हाँ बोलो. Pressure is a scalar or a vector?
Scalar.
Why?
Sir, because it cannot be defined in a specific direction. It is
So
uniform, so it
do you have any gauge which measures pressure and do you define it using the direction? Like pressure is 1 bar, 45 degree southwest. Do you mention it like that? No. So pressure is a scalar. See, the air which is inside the ball is creating the pressure distribution, right? And this is equally distributed throughout this inner surface of the ball, right? So pressure is a scalar, but when it acts on the surface, its effect is a vector, and we call that effect as a pressure force. Pressure force. So pressure force is a vector, means when pressure acts on a surface, it creates an effect, which is nothing but the pressure force. So pressure force is vector, but pressure itself is a scalar. So that is the reason why we have defined this using this type of approach, that magnitude of normal force per unit area, right? Is it clear why pressure is defined using this magnitude of normal force? And one more thing you should remember here is this word normal force. Don't just say force per unit area. Be specific. Normal force. So if you look at the element which I have taken here, this element, the direction is normal to that surface. That's why normal force per unit area. Is it clear? So if you have a surface, the normal force is nothing but the pressure force, or force created because of pressure which is applied on the surface, and this this is known to you. This force per unit area. What is this force? Is it shear force? You know this shear stress. Stress is also force per unit area, no? Force per unit area. Now what is this force? Is it normal force or shear force? Hello. So you understood the difference between the shear force and the normal force, or the tangential force and the normal force? I hope you have understood this. Now, shall I go ahead?
Yes, sir.
Okay, fine. Now, moving further, first of all, we'll derive the Pascal's law, and then we'll talk about the hydrostatic equation. Now, what is Pascal's law? Any idea? Pascal's law. Have you studied it before? Pascal's law, statement at least. So the definition of Pascal's law, or it defines like the pressure at a point in a static fluid is equal in all directions. This is the definition of Pascal's law. Pressure at a point in a static fluid is equal in all directions. Now we are going to prove this using the element which is shown on the screen. So consider element of wedge shape. This is wedge shaped fluid element. Wedge shaped fluid element from the static mass of fluid like this free surface. So I am taking any element from the static fluid at this particular location I have taken. You can choose from any other, and the shape of the this fluid element is like wedge, right? So of course you can use any other shape also, but still the Pascal's law is valid for that. So for our analysis purpose, I am taking the fluid element having wedge shape and having the dimensions delta x, delta y, and delta z. These are the dimensions of your fluid element wedge, which are shown in the diagram here, right? Now, so if I say, let us say I'm naming this triangle as let us call this as A, B, and C. So the angle ACB, this angle is theta, right? And this wedge has how many faces? कितना faces है इसको? हाँ बोलो. How many faces this wedge has?
5.
Now see, the forces which are acting on the fluid element are of two types. Under this condition. So first is the pressure force normal to the surfaces, there are a number of surfaces, so normal to the surfaces. And second is weight of the fluid element. We know this, weight of the fluid element. This is also called as a body force, in this case fluid element. So there are only two types of forces acting on this fluid element, right? Now if you look at the diagram, the pressure forces are shown here. For example, if you take this face, let us call this A, B, C, and then call this as D, E, F. For reference, I'm just putting the nomenclatures. So if I want to find out what is the pressure force on this face A, B, E, D, which is shown by this arrow, so what I have to do is I have to consider the pressure along that direction and multiply it by the area of this face. Then what I get is the pressure force acting normal to this face, right? So here I forgot to explain or mention. Let us assume that Px, Py, Ey, and this PS, these are the pressures acting along, this is your Y direction, along X direction here, and you can say along Z direction also, but we have taken this slanting edge of the wedge, and the pressure which is acting normal to this face, let us call it as a PS. That's why I said Px, Py, and Px, Py, and Ps are the pressures acting along X, Y, and S direction respectively. Clear? So how to write this term is clear to you. So you have to simply take the pressure along that particular direction, multiply by area of the face. So that will give you pressure force. This whole term is pressure force. Whole term Py into delta X delta Z is nothing but the pressure force acting on this face. As I said, pressure force is vector, that's why arrow is there. Now similarly, I can write what is the pressure force acting along Z direction on this bottom face. So this is written. You should draw this diagram and write down all this. Then and then only you will understand, otherwise not. And similarly, there is one more face on which the pressure force acts. So the pressure PS multiplied by the area of this face, delta X, delta S. Clear? So we are done with the pressure force terms. Now, second, you have to write the expression for the body force, which is nothing but the weight of the fluid element. Now, how will write the expression for body force or weight of the fluid element? Capital W. So let us say capital W is the weight of your fluid element, W. So the W will be given as the mass of fluid element multiplied by acceleration due to gravity G, right? So this will be also equal to rho into V. This is V stands for volume multiplied by G, right? So you can write this weight of the fluid element as half delta X, delta Y, delta Z into rho G, right? So this is how you can write the weight of the fluid element. Now this is written considering the third dimension, which is delta Z, right? Third dimension delta Z is considered here. In few books you will find that one dimension is taken as unity, and then only two terms are there, or two dimensions are there while writing the expression for this term. Fine. Is it clear? So this is your second force, which is the weight of the fluid element. right? Now, under equilibrium condition, these forces balance each other. That's why this element is in the position where it is, right? So I am going to simply apply the analysis which we have learned in mechanics. So I am going to write what is summation fx and equate it to 0. So I will write the expression when you write summation fx equal to 0, analyze the forces. So you will write this Py into delta x delta z, this force around x direction, right? Minus, now see which component of this force I should take along this direction. So can anybody tell me what will be that component? Follow. Component of this force. So it will be PS delta x delta s. What should I write? Follow. Sine theta, right? Sine theta. This must be equal to 0. Is it correct?
Yes, sir.
Now, yes. Look at the geometry. Look at the geometry and tell me what is this delta s sine theta. Look at the triangle and tell me this term. What is delta s sine theta? Say this edge BC is delta s. So if you see the sine theta, so this must be below. Hello. This must be delta z, right? So you can solve this expression further and you can write this Py delta x delta z. This must be equal to PS delta x, and for this I am going to put delta z. Now look at this, delta x delta z will get cancelled out, and from this expression I can write this Py is equal to PS, right? So the pressure along y direction is also equal to pressure along any random direction s which we have taken in this element. Is it clear? Just a minute. So I hope it is clear to you how we did this. Pressure along y direction is also equal to pressure along s direction. So this is we proved using the summation fx equal to 0. Now similarly, can we write the another force balance along z direction? So suppose if I write summation fz, which is our vertical direction, fz, this must be equal to 0. So now you tell me what should be the forces I should write. Tell me the terms. So the vertical force, this is positive in positive z direction. This is positive z direction, vertically upward. So this force is also positive. So I will write Pz delta x delta y, this term. Then the vertical component from this, it will be, and it is in negative direction, negative z direction. So it will be minus PS delta x delta s, and should I write cos theta or sin theta? Correct? Right? And apart from this, I have shown the body force which is acting through the center of this wedge, this body force. Now this I have written gamma is specific weight, which is nothing but this rho g. So if you want, you can just replace this by rho g in the diagram itself. Write it as rho g, right? So this is minus again in negative z direction. So minus delta x, delta y, delta z divided by 2 into rho g, and this must be equal to 0. This is what the force balance I am writing along z direction. Clear? Now again similar to the previous case, who will tell me what is this delta s cos theta? Looking at the geometry, what is delta s cos theta? Bolo.
Delta y.
Huh? Delta y, right?
Y.
So this must be delta y. And also one more thing you should remember. See, what we mean by fluid element or fluid particle. Now you should invoke the definition of fluid particle. So the definition of fluid particle is it has a definite mass. I said it has definite mass, but its dimensions are negligible. You are getting my point or not? I said it has definite mass, but the dimensions are negligible. Means this dimension delta x, delta y, delta z are very, very, very small. So in that case, the product of these three small dimensions, delta x, delta y, delta z, this is going to be very, very small. So we can neglect this term, the body force term. Is it clear? And if I solve this expression further, then I can write this Pz delta x delta y, this must be equal to Ps delta x, and for this I am going to put delta y again, right? So look at the expression, delta x delta y can be cancelled out, and again I am writing Pz is equal to Ps. This is second expression I am writing. So from this equation, call this is, let us say, equation 3, and this is equation 4. So comparing equation 3 and 4, in general, now see, the element selected was arbitrary, so you can have the element of any other shape, maybe a rectangular element you can take, and still you will end up getting the same analysis, right? So from 3 and 4 I can write this Px is equal to Py is equal to Ps is equal to Pz, any direction, right? Any direction. So what is meaning of this equation? So we have proved the Pascal's law that pressure at a point in a static fluid is equal in all directions. So pressure does not depend on direction. Is it clear? Pressure at a point is equal or same in all directions. This is what Pascal's law we have proved. Clear? Now can I go ahead?
Yes.
So what is the use of this Pascal's law?
So
So
equation 2 के यहाँ पे आपने लिखा है summation fx is equal to 0 and
you are not audible. Bolo. Summation
is equal to.
I am not getting you.
दो इक्वेशन था, इक्वेशन 3 एंड इक्वेशन 4 था, जहाँ पे py इक्वल टू ps एंड pz इक्वल टू ps किया. दोनों में जब हम लोग ने स्टार्ट किया तभी दोनों में समेशन fx इज इक्वल टू 0 है. So नीचे वाला x है,
z. See, this is z. This is z, not x. Or let me write it again. This is z, not f, summation fx. So we are analyzing forces along x and z direction only. Is it clear? See, if you refer Indian author books, this direction they have taken vertical direction as y, and this is x, horizontal direction. Okay. Hello. And this direction is y in Indian author books. So it depends on which book you are referring, but as long as you are analyzing the forces along this direction. See, if we have taken y, so convert this to y. Don't write summation fx because this direction is y as per diagram. So write summation fy, not fx. We are analyzing forces along y direction now here. So make the correction, write summation fy, and this is right, summation fz. Is it clear now? Hello.
Yes.
Is it clear? See, most of the time what we do is
Yes,
we
sir.
take x direction as horizontal, na? But in this diagram y direction is taken as horizontal. That's why I asked you to change it accordingly. Fine.
Yes, sir.
Now, moving further, what is use of this Pascal's law? Any idea? Now look at these two images or two pictures. On the left hand side, what you see is a piston cylinder arrangement, right? Piston cylinder arrangement. On left hand side, you will see the cylinder is very small compared to the cylinder on the right hand side. The piston cylinder arrangement basically. So what we can do is, using that Pascal's law, we can transmit the pressure applied at one point or the force applied at one point to the another point, right? Or reverse is also possible. Getting me or not? Hello. So idea is, you can lift a heavy object. You can lift a heavy object using a small piston cylinder arrangement like this, and the analogous what you can say, the representation is shown here on the right hand side. So here question may be asked, or a question should be asked like, is it possible to lift elephant using mouse? That should be the question we are supposed to answer. So the answer of this question is hidden in the Pascal's law, right? So what do you think? Is it possible to lift this elephant using mouse of such a small mass m1, and mass of the elephant is m2? Is it possible? हाँ बोलो. Hello. Just say yes or no, bas. Or if you don't want to interact, I leave it to you.
Yes, sir, it is possible. If you manage the area.
If you appropriately choose these dimensions d1 and d2, it will be possible to lift this elephant using that mouse of mass m1, right? So this you can say the analogy for the Pascal's law. Fine. So once again I repeat, Pascal's law is the pressure or intensity of pressure at a point is same or equal in all directions. Fine. Now can I move ahead?
Yes, sir.
Fine. Now we talked about the term pressure. We defined what is pressure using that definition that normal, it is the ratio of the magnitude of normal force to the area on which it acts, right? Now what are the units of pressure? You may be knowing units of pressure. Bolo. What is the unit of pressure?
Pascal.
Very good. Any other unit apart from Pascal?
Newton per meter square.
Very good. So 1 by 1 I'll write here. First is Pascal.
Millimeters of Hg.
Pascal, simply people write it like this, Pascal. Then और कुछ बोल रहे थे कोई? Newton per meter square, right? Then
millimeters of Hg.
Very good. Mm of Hg. Then have you seen this unit?
Bar.
kgf per centimeter square. Bar. Very good.
Bar, sir.
Bar. What is the relation between Pascal and bar? 1 bar is equal to? What is 1 bar equal to?
10 raised to minus 5 Pascal or 10 raised to 5?
10 raised to? Is it correct? बराबर है? Just tell me, is it correct or not? So 1 bar is also equal to 10 raised to 5 Newton per meter square, is also equal to 100 kilopascal, right? Correct? So note down all these. This will be required for solving numericals. And the last unit, which is kgf per centimeter square, This type of unit you will observe in the mechanical gauges which are used for measuring pressure. Laboratory gauges in laboratory gauges. On that you will see this type of scale, kgf per centimeter square. So you can convert this to Newton per meter square. How to convert? So kilogram force will be converted by multiplying with 9.81, and centimeter, you know the relation between centimeter and meter, right? So 100 centimeter is 1 meter. So accordingly you can convert this kgf per centimeter square to Newton per meter square. We will be using all these units interchangeably all the time. Fine. Now what is atmospheric pressure? Coming back to atmospheric pressure. What is atmospheric pressure? Any idea? Now where you are sitting right now, maybe in your room, there is atmospheric air surrounding and it is interacting with whatever the surfaces which are coming in contact with that air, right? So the atmosphere is exerting some sort of the pressure on the objects in which with which it is coming in contact. So the pressure exerted by the atmosphere, we simply call it as atmospheric pressure, right? What is the unit, what is the instrument used to measure the atmospheric pressure? You must have studied in physics. Instrument used to measure atmospheric pressure. Somebody told me that unit of pressure is mm of Hg, na? So it is? Bolo.
Barometer.
You may be knowing the concept of barometer, right? Now, look at this diagram. Look at this diagram. So what is plotted on the y-axis is pressure, right? And you will see 4 horizontal lines here. So this is our datum. Let's call it as a datum or reference line for us. So this represents the absolute zero or complete vacuum. Absolute zero or complete vacuum. Now, I have taken 2 points. One is point A on this line and another is point B here, right? And this line represents the atmospheric pressure, which is nothing but the local barometric pressure, the pressure read by the barometer, which is also called as the barometric pressure, right? So this is your atmospheric line basically. Fine. Now all all laboratory gauges, they measure pressure with respect to the atmosphere. With respect to this line, they measure the pressure. Fine. So looking at the diagram, it is very clear to us that the point A, pressure at point A is more than atmospheric. That's why this point is on the upper side of this atmospheric pressure line. And at point B, the pressure is less than atmospheric, right? Now, if I am measuring the pressure at point B with respect to absolute zero, then that pressure will be called as absolute pressure at point B. See, the reference line is from here. I am measuring the pressure at point B with respect to this absolute zero. Then that pressure will be called as absolute pressure at B. Let us say if I am measuring the pressure at point B with reference to atmospheric pressure, means from here, then the pressure at B will be called as the vacuum pressure or negative pressure with respect to your atmosphere. Is it clear? And look at point A. Again, if my reference point is this datum or absolute zero, the pressure measured from this absolute zero up to point A, this will be called as absolute pressure at point A. And the same pressure, similar kind of pressure, if I am measuring with respect to atmosphere, then I am going to call it as a gauge pressure at A. So understand the difference between gauge pressure, vacuum pressure and absolute pressure. And I want you to write the relation between these three. So, or write down the relation on your own. So how will represent the relation between absolute pressure and gauge pressure? Can you write on your own? Bolo, can you write it on your own? So with respect to point B and A, write down what is absolute pressure. So absolute pressure absolute pressure is equal to atmospheric pressure plus gauge pressure. Now this I am writing with respect to point A, because pressure at point A is more. So I am writing absolute pressure plus gauge pressure. Now what about point B? So at point B, the absolute pressure is again equal to atmospheric pressure minus this vacuum pressure, or if I write only plus vacuum pressure, then you should remember that vacuum pressure is a negative pressure, negative gauge pressure. Is it clear? Is it clear? So the absolute pressure at point B, you have to deduct this vacuum pressure from atmospheric pressure. So absolute pressure is less than atmospheric pressure. Is it clear? Relation between absolute pressure and atmospheric pressure. So to vacuum pressure you can call as negative gauge pressure. You should remember this. So in examination they may ask you questions maybe for 1 or 2 marks. So they may give you the pressure in absolute terms, and they may ask you to find out what is the corresponding gauge pressure, or reverse also. They may give you the gauge pressure and they will ask you to find out what is the pressure in terms of absolute, right? So all those conversions you should be in position to do it at your end. Clear? Now can I go ahead?
Yes, sir.
Okay, fine. One more thing I should mention before we proceed. As I said, in case of laboratory gauges, when the pressure you measure is above the atmospheric pressure, you will see this type of unit used, kgf per centimeter square. And whenever you are measuring the vacuum pressure using the laboratory gauge, now you will see the scale which reads mm of Hg. Mm of Hg instead of kgf per centimeter square, as the vacuum pressures are less compared to the gauge pressures. So the scale, if I draw what you can say, the gauge indicator like this, so what I observe is the pressure which is measured as kgf per centimeter square in one dial, and in another dial I will see mm of Hg. So these are the general what you can say, the units used in most of the laboratory gauges. In general, you will observe these scales. Is it clear? Hello. And by chance, if you visit our laboratory, I want you to look at the direction in which these two are measured. So it means I want you to observe gauge pressure is measured in clockwise direction, and the vacuum pressure is measured in anti-clockwise direction, or both are measured in the same direction. So that also I want you to observe in laboratory. Now can I go ahead?
Yes, sir.
Fine. Now our next point of discussion is we are going to derive this expression for the variation of pressure in a fluid at rest, right? So previously we said, using Pascal's law, that pressure at a point in a static fluid is same in all directions. So let us say we have a static fluid like this. This is fluid, and out of this I am taking one small element in the form of a parallelepiped like this, and then I am going to analyze this using the forces which are acting on it, right? And so we'll find out the variation of pressure in a fluid at rest. We said, using Pascal's law, it does not depend on x, y and z directions at a point. At a point. But what will happen if I change this point, location of the point? Instead of here, if I take the point here, then what will happen, right? Means if I say this is x direction, so I am trying to find out whether the pressure will change along x direction. Similarly, if I am taking this as a y direction, so I am shifting this point to here. Again, I will try to find out whether the pressure is varying along y direction, or if I take the third dimension z, and if I shift the point in the z direction, again I am trying to find out whether the pressure is varying along z direction or not. So at a point it is same in all directions, but if I change the point, what will be the effect? This is what I am trying to find out. Now to do that, again I am considering a fluid element of the shape of parallelepiped. Now what are the dimensions of this element? Again the dimensions of the element are delta x, delta y and delta z are the dimensions of the fluid element. And let us say the small w is nothing but the specific weight at that particular location, specific weight of the fluid, rho g. So this is what I have shown here. Now look at the coordinate system. Now I have changed it. This is horizontally is x, vertically is z, and this direction is y. Now again, similar to the Pascal's law, there are two types of forces which are acting on this fluid element. Now what is the first type of force? Bolo. The pressure forces. Pressure forces acting normal to the surfaces, 6 surfaces of this or 6 faces of this PPD, parallelepiped, right? And second is the body force, which is nothing but the weight of the fluid element, which is acting through the CG of this element from here, acting in vertically downward direction. So this component is nothing but the body force or the weight of the fluid element. So weight is specific weight into the volume of the element, which is delta x, delta y, delta z. So this is simply rho g v, vertically downward acting force, weight. Now what about the pressure forces? So for that, what we are going to do is, we will assume that the pressure at this point O, let us assume that pressure at center O is P, and then I am just taking the coordinate system x, y, z. So let us say P is the pressure at this center of the parallelepiped, right? Then how to write these terms? Now this is the pressure change along x direction, right? So we don't know whether the pressure is same along x direction or not. So I should write, or I should account for the variation along x direction, right? So how to write this term? Any idea why the term is written like this? Or any mathematical tool where you must have used this type of approach? Okay, how many of you remember Taylor series expansion? Taylor series expansion. You must have studied in M1, M2, right? Hello? Hello?
Yes, sir.
So what is Taylor series expansion? How you write it? So you write it the expression like f of x, and h is the variation, then you write fx plus h f dash x plus h square by 2 factorial into f double dash x. So that type of Taylor series expansion you write, right? Correct? Yes. So the variation in pressure P along x direction is written using Taylor series expansion and neglecting higher order terms. I repeat, this variation is written using Taylor series expansion and neglecting higher order terms. So look at this face now, this one, this face. Now this face is on the left hand side of the center point O, right? And we have to write the expression for the pressure force acting on this particular face. So how to write the pressure force term? We know this, that pressure multiplied by the area of the face. This is nothing but the pressure force. And we know that the pressure force always acts towards the surface. That's why this arrow is always towards the surface. You refer any book, you will find the direction of the pressure forces always towards the surface, right? So the pressure forces are basically compressive in nature. You can note down that. I said pressure forces are compressive in nature. Fine. So this variation is written as, now P, the pressure at this point. You are writing the variation on left hand side. That's why minus sign. Then rate of change of pressure dou P. Now along x direction. That's why I'm writing dou P by dou x. And the distance through which this change is occurring. Now what is the distance through which change is occurring? This is at the center, so half of this delta x. This is total is delta x. So half of delta x by 2 is the distance through which this pressure P is changing along x direction. That's why this delta x by 2. Now this is for the pressure term multiplied by the area of the phase, which is delta y delta z. This is how I am writing the term, left hand side term, pressure force acting on this phase. Now similarly I can write what is the pressure force on right hand side phase. Now same logic I am applying. The only difference is now this phase is on right hand side of this center. That's why instead of minus I am writing plus. So P plus dou P by dou x into the distance through which this change takes place multiplied by the area of the face, which is again delta y delta z, right? See area kaise lena hai? So you have to just remove the direction along which you are writing the variation. Suppose for x direction the face area will be yz, for z direction it will be xy, right? And for y direction the face area will be xz, delta x delta z. Clear? So similarly you can write down the remaining terms like these two and these two terms. Is it clear? So don't directly jump to this diagram. Huh? See, first you have to draw this PPD, then show the dimensions delta x, delta y, delta z, and then show this body force, then this specific weight W into delta x, delta y, delta z, and then show the 6 pressure forces on the faces of this element. Is it clear? Hello. Now can I go ahead? So once I have noted down the forces which are acting on all the faces of the element and also the body force, now it is time to analyze the forces along x, y and z direction. So what I am going to do is I am going to take summation fx is equal to 0, summation fy is equal to 0 and summation fz is equal to 0. As this is a 3-dimensional element, so I am going to analyze forces along all the directions. Now this fluid element will remain in the position where it is. For example here, only when the forces which are acting on the element are balanced. So that's why I am using this analysis, summation fx, summation fy and summation fz equal to 0. So what you will get, you just write down summation fx equal to 0. You tell me one term and then for rest of the things we will conclude. So I will write summation fx equal to 0. Tell me the terms. Bolo. So I should write. See, when you do not interact, I conclude that you are not paying attention or you don't understand at all, or you don't want to, what you can say, the interact. This is what I conclude. Bolo. So how should I write summation fx equal to 0? Now what are the forces acting along x direction here? So this is one force and this is second, right? And all other forces are in different directions. So I have to just sum up these two forces. No? So I am writing P minus dou P by dou x into delta x by 2 multiplied by delta y delta z. Now here should I write minus or plus? Bolo. Plus or minus, or whatever I have written is correct.
Yes sir, right.
Right. Now why I am writing minus sign here? Because this force is in negative x direction. See, the positive x is in this direction. No? If your force is along the negative x direction, you should account for the direction minus likha, right? So when you solve this expression, what you get is, I am just directly writing. I leave it to you to solve this further. So you will get dou P by dou x equal to 0 simply. Okay? When you write summation fx equal to 0. On similar lines, when you analyze the forces along y direction using this kind of expression, again you will get dou P by dou y is equal to 0. Okay? Fine. And the last term I should write, that's why, because there are additional forces apart from pressure forces, so that's why I'll write for this last term, summation fz equal to 0. So what should I write for summation fz equal to 0? Look at the z direction, right? So this force must be positive along z direction, no? So I should write P minus dou P by dou Z into delta Z by 2 multiplied by delta X delta Y minus P plus this dou P by dou X, dou P by dou Z, sorry, dou P by dou Z into delta Z by 2 multiplied by delta X delta Y. And apart from these two forces, vertical forces, there is one more vertical force which is body force, this one, and this is acting in negative Z direction. So it should be written as minus. Now instead of writing the small w, I am writing rho g, specific weight, rho g, right, multiplied by delta X delta Y delta Z is equal to 0. Now when I solve this further, the volume of the element delta X delta Y delta Z can be cancelled out, cancelled throughout, right? And what I get from the expression is dou P by dou Z is equal to minus rho G, or is equal to minus W, let us say, specific weight, or is equal to minus gamma, whatever notation you are using for the specific weight. This is the expression you will get. Dou P by dou Z is equal to minus rho G is equal to minus W, small w, specific weight. Is it clear? Hello. Hello. Is it clear how we derived this?
Yes, sir.
Yes, sir.
So now, if I name this expression as, let us say, 1, this as 2, and the last one this as 3. Now comparing equation 1, 2 and 3, what I conclude is pressure does not depend on x direction. Now look at the x direction. So if I have a fluid mass like this, and if I am moving along x direction like this, the pressure does not change with respect to x direction, right? Now from equation 2 I am going to write pressure does not depend on y direction. So in the same, if I move out of this screen along y direction, then also pressure is not going to change, right? So in short, I will conclude that pressure only depends on z direction, which is vertical, right? So shall I say that in a static fluid, pressure only depends on the vertical direction and not on the horizontal directions x and y. So if that is the case, instead of writing this dou P by dou Z, now why we are writing dou partial derivative? What is difference between partial derivative and total derivative? Bolo. See, if pressure is function of x alone, then I am going to write dP by dx. But if pressure is also function of y and z along with x, then it partially depends on x, y and z. No? Getting me or not? Partially depends on all the three x, y and z. So we concluded that it does not depend on x, it does not depend on y, so it only is a function of z direction. So instead of writing dou P by dou Z, I am going to write as dP by dz now is equal to minus W is equal to minus rho G. So this expression itself is a hydrostatic law. This expression is actually a hydrostatic law. Fine. So how I am going to define the hydrostatic law then? So I will say that the rate of increase of pressure in a vertical direction is equal to the weight density or specific weight, one and the same. So the rate of increase of pressure in a vertical direction is equal to the weight density of fluid at that point. Now remember the last line, I said at that point. At that point. So suppose I am taking this point, then the rate of change of pressure along the vertical direction is going to be equal to the specific weight of the fluid at that particular location or at that particular point. This is what the hydrostatic law is. Is it clear? Now, what is the significance of this minus sign? Why we are getting minus sign? See, in few books you will find that they have written the expression dp by dz as omega, w or rho g directly. Yeah. So look at the convention. See, we are taking z vertically upward as positive, right? So this minus sign indicates in a static fluid, as you go up, pressure decreases. I repeat, this minus sign indicates as you go up, pressure decreases, and as you go down, pressure increases, right? So suppose if I change the sign convention, instead of taking the origin here and measuring the z in upward direction, if I measure the pressure, let us say, if I measure the z in this direction, z dimension in, this is my reference, free surface. So it means the downward dimension I am taking as positive. So that time I need not have to write this minus w. I will simply write dp by dz is equal to w or rho g. So minus sign I can take out. Clear? So if I integrate this equation, then what I get is pressure is equal to rho g h, this expression which we have used previously. So in a static fluid, if I want to find out what is the pressure at any point like this, the only thing I should know is what is the density of the fluid at that location. G is known to me, and what is the location of this point from the free surface, H. So the moment I know these three, I can find out what is the pressure at this location using the simple formula, pressure is equal to rho g h. Is it clear? I think we are running out of time, so we should stop. We can save this. This will